So hello and good evening, a very good evening to everyone who has joined. So I'm Moitreya Bhattacharjee. I am the organizer of the UG webinar series, officially unofficially organized by the Indian Association for the Cultivation of Science BSMS cohort. So we are very glad and happy to have Javed Umar from the School of Physical Sciences, NISER today. So let me give a brief introduction of the speaker. And before that, I apologize for being a bit late in starting the meeting. Actually, I myself was in a meeting with my MS advisor. The talk was originally scheduled to begin from 7 p.m., but we got delayed by 15 minutes. The inconvenience caused is sincerely regretted. So as I was telling, let me come to a brief introduction of the speaker. Javed Umar is a 7th semester 4th year student at NISER, and a very good friend of mine. I first met Javed when I myself went to NISER in the summer of 2022 as an Indian Academy of Sciences Summer Research Fellow in the School of Mathematical Sciences. So as you can imagine, the people who are from NISER, although I was originally working in this mathematics department, I used to spend most of the days working in the lounge of the physics department in the 4th floor. So I met him at a canteen, and he was a very enthusiastic guy to interact with. So originally that summer he had went to some IIT, I guess Dhanbad, for an internship originally in high energy physics. But this year, I mean in 2023, he went to the prestigious GIFR Mumbai to work in the field of experimental condensed matter physics in the lab of Professor Koloboron Maiti. So I've always enjoyed my conversations with Javed, be it physics or non-physics. And when he requested me to give a talk in our seminar series, I was really delighted. So without further ado, I give the stage to him, and you can begin your talk by sharing your screen. Thank you so much. And if you, sorry for the interruptions, and to the audience, if you have any questions, please feel free to unmute yourselves. You can even type your questions in the chat box. The speaker may answer them during the talk or at the end of the talk. And just a small disclaimer, the entire talk will be recorded on YouTube in our official YouTube channel. Please like and share and subscribe. Thank you.
Okay, am I audible?
Yes, you're audible, Javed.
Okay, thank you, Maitro, for this introduction. Brilliant. There. Okay, my screen is visible, right?
Yes.
Okay. Okay, so myself, Javed Umar, undergraduate student from NISER Bhubaneswar, and today I will be discussing about this topological phase, how to get the topological phase in an electrical circuit. Like conventionally we get in photonic lattice or optical lattices, but now I'll discuss about this, how to get this phase, novel phase in the electrical circuit. Okay, so here is the content of my talk. First, I will briefly discuss about. Sorry. First, I will. Okay, sorry then. Yeah, I don't know how it's not visible, but I'm sharing this one. Stop presenting. Present. Ah, now now it's visible, right? Ah, okay. So again, because of this problem, let's start from beginning. So this is the title of my talk, topology, how to get topological phase, a novel phase, condensed matter physics actually, how to get this phase in electrical circuit. Okay, so here is the content of my talk. First, I will briefly introduce the SSH model, a toy model in condensed matter physics. Then, and its topological property, where is the topology hidden in this model, SSH model. And then how to simulate this model in LC or electrical circuit, and the setup I will discuss how to simulate that in the experiment, and then experimental result, whatever we got by doing this experiment, and what more one could do in future. Okay, so let's begin. So first, as I already told, first I will discuss about 1D SSH model. So 1D SSH model, the Hamiltonian of the 1D SSH model can be written like this. And if we see this pictorial picture, then there is a two orbital or atoms per lattice site, one A and B, and this hopping is V. That's why it's written V. Oh, oh, sorry, then I don't know. Now it's visible. Now changing visible, right? Okay, just wait. Entire screen. Entire screen. Now changing visible. Okay, thank you. So there is two hopping. Hide. Okay, okay, thank you, Maitra. Okay, so there is two hoppings. One is V and one is W. That's Hamiltonian is in this form. And since we are at bulk first, means like very far from this edge, so we can just Fourier transform it and diagonalize this Hamiltonian. And if we diagonalize it, then we'll get the eigen values of this Hamiltonian, and the Hamilton eigenvalues will be of this form: is under root square V square plus W square 2BW cos k. And if we just plot it as a function of k and for fixed V and W, so for first case I plotted V less than W. Here you can see, and we get a gap system like insulating states. And if we just put V equal to W, then the conduction and valence band touches, so it's just a symmetric states. And again, if we increase V greater than W or V greater than W, then again the system is gapped. So again it's insulating. So from this dispersion relation, it seems that okay, V less than W and V greater than W both are same. But okay, let's see whether they are really same or not. We'll answer shortly. Since it's just a two-band model, so two-band model Hamiltonian also can be written in this form where H HK is just a vector H whose components are in this form, and sigmas are just Pauli's matrices. And if we just plot this H X component, Y component, Y Z component, then we'll get like this three different figures for V greater than W, V equal to W, V less than W. And since that although their dispersion are very similar, but in X and HY plane, they are very different in the sense, like if we see the first circle doesn't contain origin. And if we see the last circle contains origin. And the intermediate circle just touches the origin. So to distinguish especially two, first and last, we introduce a physical quantity known as winding number, which physically just implies that whether it contains origin or doesn't contain origin. If it's contained, then it will give some value. If it doesn't, then it will give zero. So to represent this mathematically, the winding number, the mathematical expression will be like this, and where nk is just a normalized vector of hk. And as we expect from this figure also, like why we call topological trivial, this will thing again come later. But as we expect, this v greater than w case, it doesn't contain origin, so it comes zero. And for last case, v equal to v less than w, it contains origin, so it turns out to be 1. And for intermediate case, it's undefined. And the reason is that when two band touches, we have like physically we have no sense that which band we are taking. And if we see the actual formula, then there is some diverging quantities will come. That's why this v equal to w case or metallic case is undefined. Okay, so far so good. We were in this bulk system, but in the experiment we can't generate a infinite lattice or some bulk system. We have to do infinite system for this experiment purpose. So what if we choose some finite SSH chain? So the Hamiltonian will be like this. This is just a simple configuration, because uh, only the matrix, Hamiltonian matrix, is just a tri-diagonal form, and this is obvious because it's just a tight binding model. Only nearest neighbor hopping will happen, and no next nearest or further order hopping will not happen. So it's the Hamiltonian matrix is this, and to solve this with hands is very tedious work. So what one can do, just write down the Hamiltonian matrix and then put it in any non-numerical language called Python or anything. You just put and plotted the eigenvalues. I plotted for two different cases. One, I swap V and fixed W equal to 1 for 20 lattice height. I put 20 lattice height and then plotted the eigenvalues, and for V1 and swap W. So when V is less than W, for this case, first case, we get some states near to zero. Actually, these are not zero, but very close to zero. And for W means like W less than V, we get nothing. It's just open insulating states, and we get some mid gap states. Like this is known as also mid gap states because it's in the middle. So this is the eigenvalues for this finite chain, and if we just plot the eigenvector for this zero energy state, we just extract one eigenvector which is zero energy states, means like very close to zero or minimum kind of thing, minimum eigenvalues. Then we'll get this, like as a function of lattice height. We'll see that only at the edges, only two edges, the eigenvectors will have some finite amplitude, and for other cases it's just zero. And this is for V less than W. And earlier we told that V less than W case is topological. So topological case, we see some edge mode, like the eigenvector is only localized at the edge. And if we go to the trivial case, V greater than W, then we see that the eigenvectors are totally delocalized. Okay, so where is the topological connection in this model? So I just put some picture. These picture are very different, but these all are same for a topological physicist or mathematician, because these all have a common point, that all have same number of holes. If we just take first picture, second picture, third, fourth, all have one hole. So these pictures are topologically same, and this can be illustrated by using this well-known theorem in topology in mathematics, known as Gauss-Bonnet theorem. Basically, it just integrate over Gaussian curvature and get some value where G is the number of hole or genus, which is an integer quantity. So similar thing we got earlier, our winding number, well-known winding number, which we already calculated. So it just takes whether it's winds origin or doesn't winds origin. If it's winds origin, then it will give some value 1 or 2. If it winds one time, then 1. If it two times, then 2, or further order, then further values. But if it doesn't winds origin, then it will give 0. So this winding number and this G has one-to-one correspondence. So that's why the topology comes into the picture, and people call it, okay, this has some topological features or something. Okay. Okay, now this was our brief introduction of the SSH model, and now we'll discuss how to get this model in experiment, like how to simulate in electrical circuit. Okay, for that first I will introduce the circuit and graphs, like how circuit is connected to graphs. Okay, our circuit, the fundamental laws of the circuit theory is just Kirchhoff law, which we studied in school also. So this can be written in this form. And if we just write in matrix form, then it will be like this, where L is all conductance, like I equal to V equal to IR, and 1 by R terms are in L. So why graphs? Means like if we take some complicated circuit, one gives some complicated circuit, then it's not easy to write Kirchhoff law all the times and get the values easily and get the currents, voltage on whatever physical quantities we can't get easily. So that's why we introduce graphs. So here is one example. Here is one graphs where 5 nodes are there, and if we in graph theory it's well studied, the adjacency matrix, which just put the values. If the nodes are connected, then it will put 1, and if it nodes are disconnected, then it will put 0. So for this graph, the adjacency matrix will be this form. And we have another matrix in graph theory, which is called degree matrix. We just count how many times one node connected to another node. Like for first case, if we take 1 is connected to 2 and 5. So 1 is connected to 2 nodes. That's why the D turns out to be 2 for first diagonal term. So for degree matrix, we just put diagonally, and this degree matrix can be easily achieved by just summing the rows of C. If you just sum first row, second row, all the rows and put the diagonals, then you will get degree matrix. And this L, what we define for to define this Kirchhoff law, this L turns out to be D minus C. This is defined. Okay. So now we'll discuss the SSH chain, how to simulate in LC circuit. So SSH chain has two hopping parameters, namely V and W. Already I have discussed. And the another interesting property is it is symmetric. Means like energies, we have already seen that it is just symmetric around equal to 0. So these two features we have. We have two hopping parameter and E to be symmetric around 0. And SSH Hamiltonian gives us energy, means like eigenvalues. Eigenvalues of these Hamiltonians are energy. And we already got L matrix, which is just from the circuit theory, L, which is just known as Laplacian of the circuit, which gives us Y. Means like we call these eigenvalues of L to be Y. Okay. So the SSI chain, if we just plot energies, then these are symmetric around 0. Plus V plus W to minus V plus W, since there is a cost term. And okay, so to get this two information encoded, we have to encode these two information in the circuit. So how to choose the electrical component to get this two information encoded in the electrical circuit. So if we choose just two resistance as a hopping parameter, then the eigenvalues of L will be just positive. So we didn't get, or we couldn't get any negative parts of this L or eigenvalues of L. So the resistance, if we choose resistance, then we have to also put negative resistance to the circuit. So that will make our circuit very unstable. So what one can do, if we choose capacitor, only capacitor, then again same problem will arise. Only positive part will get only positive part, and negative part will get nothing. And if we choose inductors only, then we'll get only negative part, but we'll not get any positive part. So with R, C and L, with all threes, we can't encode these two information of the SSH model to our circuit. So what about L and C? If we choose L and C, then we can see that these eigenvalues are symmetric around, not totally symmetric, but we can get some positive parts and some negative parts. So L and C is, means like with L and C, we can encode these two information of SSH model to the circuit. Okay, so it seems like with choosing L and C, the problems get solved because we just encode our two well-known information of SSH model to our circuit. But we'll see that it's not the case actually. So we earlier we got that if we choose L and C as a parameter or hopping parameter in the Hamiltonian, then we'll solve our problem. Means we could encode two information of SSH model to our circuit. But there is one problem. If we choose L and C as our hopping parameter, then for a different frequency, it will act differently. Like since conductance of C is just I omega C, and for L it's just 1 by I omega L. So there is omega factor. So for different frequency, if we check for different frequency of this circuit, then we'll get different SSH model. So that's again problematic. So what we did, we just introduced our C as a hopping parameter, and the reason we could choose L also, only L or only C. We choose C because C is less parasitic and C has less internal impedance, as corresponds to L. And the circuit will be like this, and we put some inductor in the ground, because we have to somehow encode two information of this SSH model in the circuit. So that information only could be encoded by choosing C and L combination, not only C or only L. But if we choose C and L, then the problem is just about this for different SSH model at different frequency. But if we choose only C, then this problem will be solved. We'll shortly see that this problem is solved. But another problem we are creating, that we are not encoding two information of the SSH model in the circuit. So to avoid this, we are introducing L in the ground, and now we'll and this is and introduce another matrix. Earlier we had just adjacency matrix and degree matrix. Now we are introducing another matrix called W, which is the grounded part. We just carry information about grounded part, and the effective L, which we already introduced by D minus C, will be replaced by L plus W, means D minus C plus W. Okay, so for this circuit, if we just write down the C matrix or adjacency matrix, then this will be like this form. And if we just write the grounded matrix, it's like grounded matrix is a same as degree matrix kind of, but if some node is connected to the ground, then we'll put that value, and if it's not connected, then we'll put 0. And degree matrix can be get just by summing these rows, and the total J of the circuit will be in this form, where T is just C1 by C2 and omega R, which is the resonant frequency. And why you introduce this omega R? Just because if we already seen the SSH Hamiltonian, there is no diagonal parts, but our circuit has some diagonal parts. So to make this diagonal parts 0, we are introducing omega R, such that when we reach this omega R value, this diagonal entities will be 0, and it is our well-known SSH Hamiltonian. Like we had VVWW, but here we have T minus TT minus 1 like this. So now our Hamiltonian, this hopping parameter is driven by T, which is just a ratio of two capacitor to neighboring capacitor, and we put inductor just to encode this two information of this SSH model, and that's it. And so how to measure? Actually, we construct our circuit, we encode two information of SSH model, but how to measure? This is the main part. So if we already have seen this finite case we got is zero energy states, and if we plot the eigenvector corresponding to zero energy states, this just localized at the edges. So we have two information regarding finite SSH chain. So how to get the zero energy states first? So if we take Z or impedance, basically resistance, so in any two nodes alpha beta in the circuit, this will come in this form, where lambdas are the eigenvalues of this J matrix or Laplacian of the circuit, and psi i's are the eigenvectors of this Hamiltonian or circuit Laplacian, circuit Hamiltonian. And if the circuit is in topological states, we'll get a zero energy states. And if some part of this near zero, very near to zero, and this is in the denominator, so if we put very low value in the denominator, this term will blow up, means like will be very high. So only that part will dominate, and rest are the rest whatever eigenmodes are in the circuit, that will not dominate so much. So we'll get a sharp peak in the impedance because of this zero energy value, because lambda is in the denominator. So we can say, okay, we got a topological phase because we are getting a peak at the impedance profile, and so we can say it's topological. And what about the edge localization? Like we have found the zero energy states. If we measure impedance between two nodes, we get a peak. Okay, we are in the topological state. But what about the edge localization? How to get that? So to get the edge localization, we have a circuit Hamiltonian J. It's like we have already introduced J. and J is just eigenvalue equation, because if we just replace I by V by R, then we'll get eigenvalue equation. And the eigenvectors are here the voltage. So for the zero energy states, means like when we are at resonant frequency, we'll get a zero energy states, which mainly drive the circuit. So we'll find that, so we can confirm that okay, the edge states is localized in the circuit. And okay, so in this way we just set our experiment, and what result we got. So for the first part we measure the impedance, and for the first part we just we just construct our theoretical circuit, write down the Laplacian, and run it in the Python and find out the impedance value for different cases. So first case we checked for t equal to 0.05. T is just C1 by C2, and if t is less than 1, it will be topological. So we get a sharp peak near resonance, and we increase t value again to see that whether this retains or not. So if we get t 0.45, if we put, then we'll get peak, but there is some, it's like something is happening in this case, and this is actually happening because we are allowing hopping, physically meaning that we are allowing some hoppings from nearly not dimerized limit. And if we now, since we got, if t is less than 1, we get a peak, that's for sure. Means like we check. So for now we are, since for t is 0.45 and n equal to 10, and if we measure impedance between 0 to 1 to 6 node, so we'll get like this. So to get this better, we check with 20 lattice side, and if we choose 20 lattice side, then we'll get very sharp peak. Then again we checked that what if we reduce 10 values to further. If we check for 6, then we'll get, it's like there is very nothing. It's like this resonance values is just for t equal to 88.97, it just vanishes kind of thing. What about trivial phase? T greater than 1. So if we check for 1.36 n equal to 10 lattice height, and at resonant frequency there is nothing, no peak. And again we check for 20 lattice height, there is nothing. And one more point is that we are emphasizing resonant frequency because the lattice Hamiltonian or the circuit Hamiltonian is not SSH model until we reach the resonant frequency omega r. Okay, so then first we checked with Python, just construct our theoretical circuit and write down all this code and run it and get the impedance profile. But this is not so physical, like not realistic. This is just writing some codes and all that stuff. So we there is a software called LT-Spice. So we construct our circuit and checked here. So to get some more realistic picture. But the important point is when you, so far, which means like for up to earlier slide, we checked with just Python. And there is nothing, means like where we put impedance, where we put probe, where we put nothing is mentioned, and nothing is so physical. So but when you're constructing our circuit, then it's essential to make some physical picture, like where to put probes, where to measure, how to measure, these things will come. So this is our circuit. Now we have to measure the total impedance of this circuit. So what we did, we just add a shunt resistance of some values, let's say 1 ohm or something. And this shunt is not changing our lattice Hamiltonian or circuit Hamiltonian, because it is not connected to any node, it's just connected to the source. So by putting this here, we are not changing our circuit Hamiltonian. So this will not affect our measurement. So from this resistance, we are measuring the values of current, whatever current is flowing through the circuit. And since and we are measuring through 1A and ground, so we can just write it as a Y effective. And so if we just put a two probe between 1A and ground and measure current here, then we'll get, and divide by V by I, then we'll get impedance. So what about our data? So first we checked with t equal to 2.2, which is a trivial case because t is greater than 1, and then we checked for t 0.45, which is a topological case, and we see there is a sharp peak at resonance near 88 point something. And again, first we checked with t equal to 20 case, because we get a good picture in t equal to 20 case in Python. So we checked with t equal to 20 case and we get a sharp and clear pic. And then we reduce our lattice height in this LT spice, and then check with n equal to 10 case, and n equal to 10, we get nothing in trivial phase. And when we come to topological phase, we get very similar kind of behavior whatever we got in Python. Okay, so what about real experiment? Like, so far we have done in virtual laboratory with Python and with LT Spice, a well-known software for circuit design. So we did it in our laboratory, basically teaching laboratory. We construct our circuit in the breadboard, and we measure two values. For topological case, we get a peak at resonance, and for trivial case, there is no peak. And we check for t equal to 0.45 and t equal to 2.2. T equal to 0.45 means topological, so there is a peak, and that corresponds to zero energy states. And for t equal to 2.2, there is no peak because it's trivial. So our result experiment supports our theoretical formulation or theoretical expectation. Okay, so what one could do more, like, okay, so this is very cost efficient. You can see, just construct some capacitor and inductor. So people are designing every day new circuits and studies this very rich physics in very, means like, very accessible, with very accessible equipments. One can study topological phase using some optical lattice or something, but this is not easily accessible. We have to go some millikelvin or nanokelvin to get this phase, but with this we can construct easily. So people are working. In 2018, first paper came by Ronnie Thomele, and then people continuously working on this field, and now it's very active research field. So the take home message is basically, which is a paper again, but the title of a paper again. The topological circuit is nothing but a playground for exotic topological physics. Like, you can construct your own circuit. You just write down a model Hamiltonian, and on that basis you can construct your circuit and get the physics. And yeah, this is one of the very, it's like, fascinating field which can be used in numerous fields. Like, we are very, means like, we're very excited to get quantum computer nowadays, but this quantum computing or topological quantum computing, that kind of things can also be done using this circuit. Okay, so this is all about the talks. And at last, actually actually me and my friend Subhai Dikkar actually did this all this theory and experiment in our laboratory. So I must thank him to help me. And there is one PhD Bhaiya Soumya Ranjan Padi who also helped us very. And Professor Tapan Misra, who is a theoretician basically at NISER, who helps to get our checked our theoretical ideas and calculations, all that stuff. And Senapati, who is a experimentalist, with whom we also talked when we didn't get any result or something, when we get some problem. And Dr. Saraswati Mohanty, who is a scientific officer, who also helped us very, very much. Okay, so thank you all for your kind attention.
Thank you very much, Javed. It was really a very wonderful talk. Any questions or comments from the audience? So if no, I personally have a few. So first of all, like, I personally got many ideas from your lecture. So the things which I wanted to mention is that, so first let me ask my question, then I will just give my comment. So could you please go to your so like the slide, there's a slide before this one here, the slide before what's new in the plot.
This one.
Yeah, this one, yeah. So my
Yeah.
precise question over here was that, so you have given a picture of your experimental setup from your lab, which you told. And
Hmm.
so my question is that you arrive at these two different graphs from two different approaches. Like you apply, like you arrive at the topological circuit one from the Hamiltonian which you construct, and the trivial circuit one from the experimental setup one. Is this true?
No, no, both we construct two different circuit like uh, so here is
Okay.
actually schematics of experiments, experimental setups. So the hopping is T. If we write down the Hamiltonian, T is the hopping parameter,
I see.
and this J will be same as the our model Hamiltonian, SSH Hamiltonian. If we reach this resonant frequency, omega,
I see.
if we put omega, then diagonals will be 0, and T is just C1 by C2,
Hmm.
and this T is equivalent to SSH models V. V. See, there is a V, and diagonals are 0, V.
Yeah.
And in circuit, there is a T. And another hopping is driven by 1. So as long as T is less than 1, we are in topological phase. And
Okay.
when T is greater than 1, we are in trivial phase. And
I see.
this T is driven by C1 by C2. So, and our circuit is C2 C1 is like this. So if we just swap our two capacitor, same circuit, just swap two capacitor, then we are at
Yeah.
trivial, because for one case if C1 is C2 is less than 1, then other case will be greater than 1.
Greater than, yeah. Yeah.
So yeah, so we did this like for first case we construct topological circuit, then next we just swap the capacitor. So it's just trivial.
I see. I see. Okay, nice.
Okay.
Fantastic. Yeah.
So any more
Um,
question?
yeah. Yeah. Regarding the mathematical connection which you mentioned, it's indeed very rich actually. Like, for example, I have personally subscribed to the Harvard CMSC YouTube channel, which is a Center for Mathematical Sciences and Application. And every day or two, I just get talks which are focused exactly on the slide which you have just displayed, the topological connections between very classical areas of maths like topology, differential geometry, and condensed matter physics, which is a very emerging field. Like, I personally
Hmm.
know a few people like this Professor Xiao Gang Wen at MIT, who is very much active in
Exactly.
this area. Yeah, a lot of the thing which like interests me the most is that a lot of very different kind of mathematics is coming into the play. And as you may be aware, I am working a bit in theoretical high energy physics, and so in it's like wonderful to see many string theorists also applying their kind of ideas into strongly correlated systems, and slowly they are approaching fields which you just
Yeah.
talked about. Like,
True. True.
so
Yes.
that's also another avenue. So it's very, very
Even
interesting. There are people
strongly
like,
correlated systems are not exactly solvable. So where actually topology means like I have heard this one. Not I don't know whether it's very true or not. This first when topology comes into the picture, people just give this name topology to gain some public attention. There is nothing topology or something. Just put the name topology to get some public
yeah,
attention,
I understand that. Yeah,
and
but
then and then
personally,
people
I get that.
realize, oh,
Yeah, yeah,
and
say,
then
please.
people realize, yeah, there is really something topological thing is happening.
That's
But
true.
at initial days, just people gave this name to get some public attention.
That's true. That's true. But personally, I can say that for me, the connection was not never really very non very like what to say very indirect, because whenever I'm like trying to imagine any particular form of structure of matter, it has a geometric shape. So like for me, I thought that some mathematical formalisms like this might someday come into the picture, and then I was quite excited to find various theoreticians also using tools using to like describe these
Yeah.
systems. There are people like there are many well-known string theorists who are publishing a huge number of papers in condensed matter physics, like Nathan Seiberg from IO,
Nowadays,
Dan Trade, who
so
just
many
shifted
string
to
theorists are
Harvard. Yeah,
publishing
yeah.
papers.
Yeah. That's pretty interesting to see. And the last connection which you mentioned, quantum to the quantum computer, of course, that's very interesting. I have heard a lot of talks on it, but I personally don't know much about it. But it will be interesting if some link is found in the future between the two, and we can have a quantum
Yeah,
computer
yeah,
using this.
that will be very interesting because
Yeah,
it's just a simple circuit, and so rich physics is encoded in this simple
yeah.
circuit.
Like people are kind of now shifting from traditional engine, like you can say engineering kind of view of viewing circuits in some way to more physical and more mathematical kind of view to explore the properties of the circuits.
Yeah, exactly.
So, any more questions from the audience? You can just feel free to unmute yourself or just type in. We're just waiting for a minute.
Yeah, I have a question. What was equivalent to the edge states in your this circuit thing?
Yeah, air state is equivalent to the voltage basically. If we just measure voltage at different nodes, we'll get that same kind of behavior like air state. What is
So the
it?
voltage will be high at those
Voltage
the
will be high at the first node, means like A sublattices. Uh, is the picture? Voltage will be high at A sublattices
yeah,
and
yeah.
low at B sublattices. And first, and there is some law, V is V naught to the power x minus 1. This kinds of law will follow. It will follow this kinds of law, this
So
voltage profiling.
did you measure like in your circuit that the voltages are high at the edges or something? How did you like?
We actually measure the voltage, but since we construct our circuit in breadboard and breadboard has some internal impedance, so
Yeah,
up to 3 lattice we can see that, and then it's like there is some, I don't know, means like there is some problem because of the internal impedance. So since that data is not complete, so I didn't put it in the slides. But we see up to 3 lattice sites, and after 3 lattice sites, it's like because of the internal impedance basically, because breadboard has some internal impedance, so that's why we didn't see after 3 lattice sites, but up to 3 lattice sites we see the voltage profiling.
okay, all right.
Any more questions or comments? Okay, so if not, then let us thank the speaker once again. Thank you so much, Javed, for sharing your work, and thanks a lot to the audience for your kind attention. And as said before, we will just upload our talk in our YouTube channel very soon. From there, you can upload, you can just view it at any time. So thanks a lot, and good evening to everyone, and thanks for joining. Yeah.
Yeah, thank you again, thank you all.